Hello, in this video I'll be working through Unit 1 homework problems 4 through 8. And in number 4 we're evaluating limits. So part A asks us to find the limit of f of x as x approaches negative 5. This is a two-sided limit, so we will have to check from both directions. Here's our x value of negative 5. So as we approach that x value from the left-hand side, the function value, or the y-coordinate, is getting closer and closer to 5. As we approach from the right-hand side, we are also approaching that same y value of 5. Therefore, our limit is equal to 5. Part B, find the limit of f of x as x approaches negative 3. So here's negative 3. As we approach from the left-hand side, our function is getting closer and closer to infinity. As we approach from the right-hand side, our function is approaching negative infinity. So our limit does not exist for a couple of reasons. First, the limit from the left-hand side is not equal to the limit from the right-hand side, so we would say the limit does not exist. But also, if the limit is infinity or negative infinity, we can say the limit does not exist because we're not approaching a finite value. Part C, find the limit of f of x as x approaches 3 from the right-hand side. So here's 3. From the right-hand side, our function is approaching a y value of positive 3. Part D, find the limit of f of x as x approaches 4. So here's 4. And this time we're looking for a two-sided limit. So as we approach from the left-hand side, we're getting closer and closer to this y value of 2. As we approach from the right-hand side, we are also getting closer and closer to this y value at 2. So our limit is 2. Part E, find the limit of f of x as x approaches negative infinity. So an x value of negative infinity is way out here. Where is our graph going as x approaches negative infinity? Well, it is approaching this horizontal asymptote right here at 2. And part F, find the limit of f as x approaches infinity. So infinity is way out here. As x approaches infinity, our function is approaching infinity. Number 5, find the limit of f as x approaches negative 4. This is a two-sided limit. As we approach negative 4 from the left-hand side, the function value is approaching negative 6. As we approach negative 4 from the right-hand side, the function value is approaching, we'll say, approximately negative 2.8. Since the left-hand limit and the right-hand limit are different values, we say the limit does not exist. Part B, find the limit of f as x approaches negative 4 from the left-hand side. From the left-hand side only, our function is approaching negative 6. Part C, find the limit of f as x approaches negative 3 from the right-hand side. Negative 3 from the right-hand side, our function is approaching 0. Part D, find the limit of f as x approaches 3. This is a two-sided limit, so we need to check both directions. From the left, as x approaches 3, y approaches negative 6. From the right, well, we can't really approach 3 from the right. You might want to say we're approaching 3 from the right here, in which case the graph is approaching negative infinity. However, the idea behind a limit, if we say the limit as x approaches 3 from the right, we should be getting closer and closer and closer to 3. So values like 3.01, 3.0001, 3.000001, and there are no function values that close to 3. That's not part of the domain of this function. There's just a huge gap here. So this limit does not exist. Part E, find the limit as x approaches 4 from the left-hand side. Well, we have a similar problem. If we try and approach 4 from the left-hand side, there are no values that are really close to 4 because there are no domain values between 3 and 4. The function is not defined for x values between 3 and 4. So we would say that limit does not exist. And part F, find the limit of f as x approaches infinity. As x approaches infinity, our function just approaches this horizontal asymptote here at 3. So that limit is 3. Number 6, we have the function f of x equals the quantity 16 minus x to the fourth over the quantity x squared minus 4. Part A asks, what is the domain of f? So the domain would be all real numbers except those values that would make the denominator equal to 0. So if we solve x squared minus 4 equals 0, we get x equals plus or minus 2. Those are the values that are not in the domain. Okay, so my domain, if we're using interval notation, we want all real numbers except for plus or minus 2. We would say negative infinity to negative 2, union, negative 2 to 2, union, 2 to infinity. Or I could more simply just say the domain is all real numbers x such that x is not equal to plus or minus 2. Part B, use a table of values of x near a equals 2 to estimate the limit of f as x approaches 2. If you think the limit exists. If you think the limit doesn't exist, explain why. So let's set up a table. We know that we want to approach 2 from both directions. So x values, maybe we'll start, we want to be close to 2, so we'll start at 1.9. We want to get even closer to 2, 1.99, and even closer to 2, 1.999. We're trying to find the limit as x approaches 2. So we also want to come from the right-hand side. We want to be really close to 2 here. We'll do 2.001, 2.01, and 2.1. And then we have our f of x values. So using a calculator, we find that f of 1.9, negative 7.61. F of 1.99, negative 7.96. F of 1.999, negative 7.996. So these values seem to be approaching negative 8. Let's see what happens as we approach 2 from the right-hand side. At 2.1, our y value is negative 8.41. At 2.01, f of 2.01 is negative 8.04. F of 2.001 is negative 8.0004. So it also appears that we're approaching negative 8 from the right-hand side. Now, what is happening at 2? If we go back to our function and we substitute 2 in for x, we see that the function is actually undefined when x is equal to 2. But numerically, we see that we are approaching a function value of negative 8. So we would say the limit as x approaches 2 of our function f of x is equal to negative 8. Part C, use algebra to simplify 16 minus x to the fourth over x squared minus 4, and hence work to evaluate the limit of f as x approaches 2 exactly if it exists. So 16 minus x to the fourth is the difference of squares. It can be factored as 4 plus x squared times 4 minus x squared, and 4 minus x squared is also the difference of squares, 2 plus x times 2 minus x, over x squared minus 4 factors as x plus 2 times x minus 2. And we have some common factors here that are going to cancel out. 2 plus x and x plus 2, that's a common factor. 2 minus x and x minus 2, those are opposites. If I factor out a negative 1 from 2 minus x, I get negative 1 times the quantity x minus 2. So these cancel out, leaving a negative 1 behind. So this expression simplifies to negative 4 minus x squared. And our denominator has completely canceled out. Now, when you have these common factors that cancel out, or that can be removed. This is a removable discontinuity, or a hole in the graph. So there is a hole in the graph when x is equal to 2 and when x is equal to negative 2. So we are finding the limit as x approaches 2. That's a value where there's a hole in the graph. So the limit actually does exist as we approach 2. If we substitute 2 into this new expression, so if we find the limit as x approaches 2, not of f of x, but the simplified version, so negative 4 minus x squared, that limit is equal to negative 4 minus, and then 2 squared is 4, or negative 8. So this confirms the result we got from our table. Part D, true or false, f of 2 equals negative 8. F of 2 does not equal negative 8. As we just said, there is a hole in the graph when x is 2. So since x equals 2 is a removable discontinuity. That value is not part of the domain of our function. That would be another good explanation. Part E, true or false? 16 minus x to the fourth over x squared minus 4 is equal to negative 4 minus x squared. Okay, so we're asking, is 16 minus x to the fourth over x squared minus 4, is that equal to the expression we got when we simplified it, negative 4 minus x squared? Well, they are equal for all values of x except for x equals plus or minus 2. And then part F, based on all of your work above, construct an accurate labeled graph of y equals f of x on the interval from 1 to 3. We know the limit of f as x approaches 2 is negative 8. So I'm just going to place this point here and call that negative 8. And since this limit exists, the function must be approaching negative 8 from both sides. Now the graph of this function will look like the graph of negative 4 minus x squared, just it has a hole right here. So negative x squared minus 4, that is a parabola that opens down, right? And it's been shifted down 4 units. So its vertex is here at negative 4, and then it's opening down. So something like that. Number 7, g of x equals negative absolute value of x plus 3 over x plus 3. Part A asks, what is the domain of g? So the domain here would be all real numbers except those values that make the denominator 0. So all real numbers except x equals negative 3. Part B, use a sequence of values near a equals negative 3 to estimate the limit of g as x approaches negative 3. So we're going to set up a table similar to what we did in the last problem. And we want to approach negative 3. So we'll start with negative 3.1, then we'll get a little bit closer, negative 3.01, then we'll get even closer, negative 3.001, and that's pretty close to 3. And then we'll approach 3 from the right-hand side. So we'll have negative 2.999, negative 2.99, and negative 2.9. So let's look at a table of values for x and then g of x. Negative 3, not positive 3. So at negative 3, g of x is undefined. The negative 3 is not part of the domain for the function g of x. But what happens as we get close to it? Now you can use your calculator or you can simplify these by hand, but g of negative 3.1 is going to give us 1. G of negative 3.01 is 1. G of negative 3.001 is 1. g of negative 2.999, negative 1, g of negative 2.99, negative 1, g of negative 2.9, negative 1. So the limit appears to be 1 as we approach negative 3 from the left-hand side, but negative 1 as we approach 3 from the right-hand side. So it seems, based on the table here, that the limit does not exist. Part C asks us to simplify the expression for g of x using algebra. Well, to drop absolute value, we can replace it with parentheses and a plus or minus in front. So that might look a little bit strange here. We've got minus, plus or minus, x plus 3 over x plus 3. But think about it this way. If we go back over here, if the expression for x plus 3 is positive, then we can simply drop the absolute value signs altogether. And we would have negative 1 times x plus 3 over x plus 3. So that's going to equal negative 1. So it equals negative 1 if x plus 3 is positive. Or what if x plus 3 is negative? So again, thinking about our absolute value here, if x plus 3 is negative, when we take the absolute value of it, what we're doing is multiplying the x plus 3 times negative 1 to make it positive. So in that case, we would have negative x plus 3. And that double negative is going to make it positive. And then when we have over x plus 3, that's just going to equal 1. So it's going to equal 1 if the expression x plus 3 is less than 0. Now, if I solve this inequality for x, I would, here if I subtract 3 on both sides, I'm going to get x is greater than negative 3. And down here, if I subtract 3 on both sides, I'm going to get x is less than negative 3. So let's write this now as a piecewise equation. G of x equals 1 for x values less than negative 3, and it's equal to negative 1 for x values greater than negative 3. It's undefined at negative 3, so we don't have to include that. But I guess we could, if we wanted to, we could say undefined when x equals negative 3. And this confirms what we suspected, that the limit doesn't exist, because the limit from the left-hand side is 1. The limit from the right-hand side is negative 1. So I'm going to go ahead and write that. The limit of g of x as x approaches negative 3 does not exist. Part D asks, true or false, is g of negative 3 equal to 1? Well, g of negative 3 does not equal 1, since negative 3 is not part of the domain for the function g of x. E asks, is negative absolute value x plus 3 over x plus 3, is that equal to negative 1? Well, sometimes it is, but not always. We saw that sometimes it's equal to negative 1, and sometimes it's equal to positive 1. It's only equal to negative 1 when x is greater than negative 3. So that is not necessarily true. And finally, part F, we're going to construct a graph for y equals g of x on the interval from negative 4 to negative 2. So x, we have g of x, and we know something interesting is happening at negative 3. So at negative 3, the graph is undefined, but when x is less than negative 3, the function value is equal to 1. So we can show that like that. And when x is greater than negative 3, the function value is equal to negative 1. And finally, we're asked to write a sentence to explain what we know about the limit of g as x approaches negative 3. So again, we could say the limit as x approaches -3 of the function g of x does not exist. For number 8, we're going to sketch a graph that has all of the following properties that are listed here. So first of all, f of -2 is equal to 2. F of -2 is 2, so we can plot that as a point on the graph. The limit as x approaches 2 is 1. So the graph isn't actually approaching this y-coordinate on either side. If the limit exists, then it's approaching the same value from both directions. So it's approaching 1, which puts a hole in the graph right here. And the limit, since the limit is 1, when I draw this graph, it's going to be somehow kind of connected to this hole on either side. So we'll come back to that. Our next clue here says f of -1 equals 3. So -1, the function value is equal to 3, and the limit as x approaches 1 is equal to 3. So the limit does exist, and it's equal to the function value here. Okay, so we could maybe connect it something like this, right? And then really, you could do whatever you wanted. On the left side of -2, we could have it coming down from the top, or we could just keep going, something like that. Okay, then our next clue, f of 1 is undefined. So at x equals 1, we might have an asymptote, we might have a hole in the graph, there might just be a break in the graph there, not sure. But we do know that the limit as x approaches 1 is equal to 0. If the limit is equal to 0, then the graph has to be approaching 0 on both sides, although it is not equal to 0 when x is 1. So I'm just going to connect that up, something like that. And our final clue, f of 2 equals 1. So we have a point on the graph here. And the limit as x approaches 2 does not exist. The limit as x approaches 2 does not exist. So the graph is not going to pass through this point. There's a few things we can do. We can just leave this huge gap here and maybe just do something like that. Or I could even maybe just continue this part of the, oh right, we can't leave a gap there because as x approaches 1, the limit is 0, so it has to be connected to the on this other side. So we'll just do something like this. And for this last problem, again, we're going to sketch the graph that satisfies all of these criteria. G of -2 equals 3. G of -2 equals 3, so we can plot that point. G of -1 equals -1. G of 1 equals -2. G of 2 equals 3. At x values of -2, -1, 1, and 2, the limit as we approach each of those values for the function g is equal to just the y-coordinate of g. So the limit exists at each of those points that we plotted. The limit exists, so we have to pass through those points from both directions. So it looks like we might be able to just draw like a parabola opening up, except that we're told the function is undefined at 0. So there could be a hole in the graph at 0. However, we're also told the limit doesn't exist. And if it's just a hole in the graph, that doesn't necessarily mean the limit would not exist unless there is a jump discontinuity. So it could also be an asymptote. And I think that sounds interesting. So I'm going to graph it as an asymptote. Again, there's not just one right way to draw this graph. So I'm going to try and approach that asymptote here from both directions. I'm passing through the points that I plotted because the limit exists at those points. And on the other side, we're approaching that asymptote as well.